Welcome to the class, students. In today's class, we'll look at the topic Bayes classifier for a Gaussian distribution under the main heading Relation between Perceptron and Bayes classifier for Gaussian environment. We'll consider the two-class problem, that is C1 and C2, for which the underlying distribution is Gaussian. That is, the input feature vector X is having a pattern which is having a Gaussian distribution. Let us consider for the class C1 and for the class 2, the mean values are represented by mu1 and then mu2. But the covariance matrix of the X is same for both the classes. That is, the mean value is going to differ between class C1 and C2, but the covariance is going to remain same. For both the classes, will consider the covariance value as C. That is, here for the class C1, we'll consider the expectation of the input feature vector, that is the average value is mu1, and then the expectation of x minus mu1 multiplied by x minus mu1 transpose, which is going to give the covariance matrix that we'll consider as C. Similarly, for the class 2, the mean we'll consider as mu2 and the covariance as the same, that is the C. And also we'll assume the covariance matrix C is non-diagonal, which means that is the samples drawn from the classes C1 and C2 are correlated. That is, say if it has the features x1 and then the x2, and x1 is the tumor radii and x2 is the tumor texture, then these two features are related if C is a non-diagonal matrix, that is a covariance matrix, means that is both the features x1 and x2 are correlated. And also we'll make assumption that is C is non-singular, that is a covariance matrix is non-singular, which means that inverse of the matrix exists, that is C inverse exists for the covariance matrix. Now, we'll consider the conditional probability density function of X as a multivariate Gaussian distribution. Because when we take the input feature vector, it is an m-dimensional and it will be having the m features, that is x1, x2 up to xm. Now, if the m feature vectors are there in a given input features, then the probability density function will be given by 1 divided by 2 pi of m by 2, because m dimensional. And next, it is a determinant of the covariance matrix to the power of 1 by 2 and exponent, and within the exponent the terms are minus 1 by 2 x by mu I transpose C inverse and multiplied with x minus mu I. Here I is going to take the value 1 and 2 because we have considered C1 and the C2 classes. We'll also make assumptions that two classes C1 and C2 are equiprobable. That is, both have the equal probability of occurrence. That is, if we take class 1 as benign and class 2 as malignant, if there are 6 samples in the benign, then if there are 6 samples in the malignant, then the equiprobability indicates it is 0.5 and 0.5. That is the prior probability of the benign and then the prior probability of the malignant will be the 1 by 2 or 0.5. We'll also make assumption that misclassification carry the same cost. Therefore, here C21 and C12 are one and the same, and no cost is incurred on the correct classification. Therefore, C11 and C2 are 0. Now we have to design the Bayes classifier for a two-class problem. We'll take the likelihood ratio of the Bayes classifier, which tells lambda of x is equal to P of conditional probability of x given C1 divided by conditional probability of x given C2. And now we will take the probability density function for both the classes, and then we'll find out what is the expression we are going to get now when we divide the probability density function of the class 1 over class 2. Now when we take this term and then substitute in lambda of x, lambda of x, this term will get cancelled because numerator is also going to have the same term and the denominator is also going to have the same term. And we have assumed the covariance matrix is same for both the classes, that is C1 and the C2. Therefore, in the numerator, we'll be having exponent of minus 1 by 2 x minus mu1 transpose C inverse x minus mu1. Because numerator is for the class 1, because what we had is lambda of x is equal to P of x C1 by P of x C2. Therefore, denominator will be equivalent to the term for the class 2. Now, we will take the natural logarithm on both the sides. Uh, Therefore, the term on the left side will be the log of lambda of x, and on the right side, that is this, because of the log, the natural logarithm, these exponents are going to get cancelled out, and this denominator term will goes to the numerator, because it is e to the power of a and e to the power of b is equivalent to e to the power of a minus b. And therefore we will be having now the term the log lambda of x is equal to minus 1 by 2 x minus mu1 transpose multiplied by covariance matrix inverse multiplied by x minus mu1 plus 1 by 2 x minus mu2 transpose whole term multiplied by the invariance matrix and then x minus mu2. And now we will take further this term which is there in the first term here. And now in this one, the first term is x minus mu whole transpose. We can write it as x transpose minus mu1 transpose. Now we will expand this term where we'll replace the first term with x transpose minus mu1 transpose, and this one C inverse x minus mu1. Now we will take these terms one by one inside. Therefore, first term will be x transpose C inverse x, and second term will be, that is mu1 transpose C1 C inverse x, because this term when we take inside it becomes this one. And then similarly this term will be, that is here mu1 transpose C inverse and then mu1 b, uh, x x transpose C inverse mu1, because this term has to go inside. And now the last term it becomes, that is mu1 transpose C inverse and mu. That is, we are taking this terms inside here for every term and then we are expanding. Now we got the 4 terms. Now we'll look at how this is going to get simplified. Now in this one, this term when we take actually, that is x is nothing but an m cross 1 matrix, mu1 is also m cross 1 matrix, C inverse, that is covariance matrix inverse, is m cross m. Now when we take all this thing, that is 1 into m into m and m into m into 1, it is going to become 1 cross 1, which is going to result in a single number, that is scalar. Similarly, when we take this one, that is mu1 transpose C inverse x, and their sizes are 1 cross m cross m and m cross 1, and it will result in 1 cross 1, which is a scalar number. That is, this both terms will result in some one number value. That is when we take it. Therefore, what we will do is we will equate that two terms as one single term, because this term that is x transpose C inverse mu1 and mu1 transpose C inverse x are going to result in a scalar. Therefore, we can equate. Therefore, when we equate it to mu1 transpose C inverse x, it becomes minus 2. That is, this term also we are taking it as mu1 transpose C inverse x. Therefore, it becomes minus 2 mu1 transpose C inverse x, and the first term which we had will remain same as it is. The last term also will remain as the same. Now taking this equation forward, that is for the this term we have simplified it to this one. Similarly, the second term which we had in log lambda of x, that also will get simplified as this one. this term, which is with respect to the mu2. That is, this becomes x transpose C inverse x minus 2 mu2 transpose C inverse x plus mu2 transpose C inverse and mu2. Now we will take this whatever we got, that is a simplification for both the terms, that is this term and this term what we got, that we will expand it in the log lambda of x, originally what we add on the top here. Therefore, this becomes minus 1 by 2 and this terms, and then plus 1 by 2 this terms, what we got under the simplification. Now, taking this equation forward, now when we add up these terms, here we have minus 1 by 2 x transpose C inverse x, this one, and here it is plus 1 by 2 x transpose C inverse x. Therefore, this term and this term will get cancelled out. Now, we'll look at the next one. Now, when we take this minus 1 inside here, that is this term 2 will get cancelled out. Similarly, when we take this one, this 2 term will get cancelled out. When it can get cancelled out, this becomes what? Mu2 transpose, and then this becomes mu1 transpose. That is, we know that is mu1 transpose and mu minus mu2 transpose. We can write it as mu1 minus mu2 whole transpose. Therefore, this term now it will be, that is mu1 minus mu2 transpose multiplied by C1 C inverse x, because this last term what we had here is C inverse x. Now we'll look at the last term what we had, what we have in this equation, that is mu1 transpose C inverse mu1. Similarly here mu2 transpose C inverse mu2, and this 1 by 2 will be inside actually. Therefore, this becomes 1 by 2, and then this minus here it is minus mu1 transpose C inverse mu1, but this mu2 transpose C inverse mu2 we are going to get here. That is, finally the expression for the log lambda of x is this one what we are seeing. We'll just keep this equation. And now under the base classifier, we had this xi term under the base classifier. We'll reconsider once again this one. And now under this thing, we have considered, that is both classes are going to have a equiprobable, that is prior probability of both the classes are same, that is 1 by 2. Correct classification is going to have a zero cost. Incorrect classifications are going to have the same cost. Therefore, now when we substitute, that is this P1 and then the P2 are going to get cancelled out, because this expression xi equal to P2 of C1 minus C2 divided by P1 of C21 minus C1, we got it under the base classifier. Now, when we consider this P1 and P2 are equal and it is equal to 1 by 2, this term will get cancelled out. C22 and C11 are 0, therefore it gets cancelled out. And C12 and C21 are 1 and the same, therefore it gets cancelled out. And when we take the log of xi term, it is going to become log of xi equal to 0. That is, this is the threshold test what we have taken under the base classifier. Now, the log lambda of x, we got this expression. Now, this expression, we can equate it to the perceptron equation what we had, y equal to w transpose x plus b. Now, here y is going to take log lambda of x, and w, the weight vector transpose, equivalent to c inverse mu1 minus mu2, which we have in this expression here, that is log lambda of x. And now similarly for the base term, bias term, it is 1 by 2 mu2 transpose C inverse mu2 minus mu1 transpose C inverse mu1. The bias term is going to take this particular value which is shown here. Now, why we have taken log xi equal to 0? Why we needed that one? Because if we don't take this particular condition, then our perceptron equation was what we had, that is w weight vector transpose x plus b. And we have to, when we have to make a decision, we have to consider some constant, but at that time we have to make whether it is greater than or less than, we will not be knowing. Therefore we made the boundary decision as log xi equal to 0. That is with this step that the constant becomes 0, which is going to give the form which is equivalent to the perceptron form. By making log xi equal to 0, Bayes' decision rule reduces exactly to the perceptron equation. That's why we have made log xi equal to 0. Now we can consider the Bayes classifier for Gaussian distribution is equivalent to the signal flow graph of the Gaussian classifier, where the inputs for the perceptron are x1, x2 up to xm, and weights are w1 up to wm, bias is b, and the output is y. Y here is log lambda of x, and then weight matrix is C inverse mu1 minus mu2. Bias term is, that is 1 by 2 mu2 transpose C inverse mu2 minus mu1 transpose C inverse mu1. Now, on the basis of this equation, what we have, that is y equal to w transpose x and b, we may now describe the log likelihood ratio test for the two-class problem as follows. If the output of y of the linear combiner is positive, assign the observation x to the class C. Because what we had, lambda of x, we had p of x c1 divided by p of x c2. Now we are checking whether which one is greater. That is, if it results, that is p of x, that is if this is a positive term, what it means, if it is a positive term, then px of c1 will be greater than px c2. That is, if this division term results in a positive term, we have to decide, that is, this x input feature is going to belong to the class C1. Otherwise, it tells that is the input feature x is going to belong to the class, that is C2. This is the that is this is how we are going to tell the Bayes classifier is equivalent to the perceptron, or the Bayes classifier reduces to a form which is equal to perceptron under some assumptions.